afternoon, ladies and gentlemen. My name is Johannes Laur. I'm a PhD student at the Space Systems Engineering Research Group. And today, I'm going to take you on a journey on atmospheric re-entry and how we are beating radio communication blackout. Atmospheric re-entry is by far no trivial task. It is one of the most critical phases during a space mission. Do you know how fast re-entry vehicles are? They have a velocity of around 25 times the speed of sound. And do you know what happens at such high velocities? The air around the spacecraft is getting really hot due to friction. We are talking here of temperatures of 10,000 degrees or higher. That is almost as twice as hot as the surface of the sun. So now imagine you're sitting in a tin can dashing down to Earth at a velocity of 8 kilometers per second. The air is getting thicker and thicker. Your spacecraft is shaking. It's terribly loud. You can see the flames through the window, and you're hoping the the heat shield of the spacecraft is not going to fail. To make things worse, the communication to the ground station is getting noisy and eventually fails. Now, this is radio blackout. Nobody can hear you scream or knows exactly where you are, or even if you're fine. Seems terrifying, isn't it? Now, what I want to find out within my research is what is happening to the radio signals in this plasma cloud around the spacecraft, because avoiding radio blackout communication can be life-saving. To do so, I am looking into this plasma cloud, and I am analyzing how the radio signals are interacting with the plasma, or to be precise, with the free electrons in the plasma, because those free electrons in the plasma are mainly responsible for the signal attenuation, meaning the higher the number of free electrons are in the plasma, the more the radio signal gets bent, disturbed, or even totally blocked. But figuring out what is happening with the signal in the plasma is not the only thing I want to find out. The next step would be to actively manipulate the plasma. And what do you think? How could we do that? Magnets. My research is part of the Magneto-Hydrodynamic Enhanced Entry Systems for Space Transportation project, in short MIEST. Within MIEST, we are using a superconductive magnet to create a very strong magnetic field. We are talking here of at least 1 Tesla, which is, by the way, 20,000 times higher than Earth's magnetic field. The electromagnetic waves emerged from antenna are interacting with this magnetic field, and a so-called magnetic window is created. That is what you can see here on the slide. But even if the electromagnetic waves are able to leave the plasma cloud through such a magnetic window, we have no idea what the signal quality actually looks like. Therefore, we also need to analyze how is the signal quality becoming while the signal is propagating through this plasma. This becomes a very interdisciplinary problem. The physics are not trivial. They are not linear. No, the physics are scarily complicated. I just faced that last week when I had to finish my first report. But I can tell you one thing. I'm in my second year of my PhD now, and I'm going to solve it. Thank you for your attention.
Fantastic, Lars. I think you've been channeling. Do you watch Lost in Space? You've been channeling the mother in Lost in Space. This is very good stuff. I think you should talk to them.